Hi everyone, we are Amulya, Dhruv, Sam, and Meghasha. Our ECE5775 final project is a sparse matrix dense vector multiplication or SpMV accelerator using Vivado HLS. We have also implemented a PageRank algorithm which uses the SpMV accelerator that is run on the Xilinx Z board. We were able to speed up the SpMV kernel using several code optimization techniques and Vivado HLS pragmas. We have also analyzed the speedup when running the kernel on the Z board.
Sparse matrix, by definition, means fewer non-zero elements in the matrix. The sparse matrices are a key part of several data-driven algorithms like page ranking and biogenetics. Inherently, algebraic operations for floating points are memory-bound, which results in low operational intensity. Since floating point is a key data type used in graph algorithms, these applications would improve multifold even with simple optimizations of the SpMV kernel. Another challenge with SpMV is irregular data access pattern due to sparsity, which sets ceiling on the parallelism. While sparsity was the challenges mentioned above, it also brings a potential to accelerate by exploiting the sparse structure. Hence, this made it a lucrative topic for a design project.
In order to address the challenges resulting from irregular data access patterns and reduce the number of memory accesses, we chose to reformat our sparse matrix using coordinate ordering formatting, shortly referred to as COO. Here, we transform our matrix into three smaller arrays for row, column, and data. Each corresponding element in each array corresponds to a single non-zero entry in the matrix. As part of this formatting, we then were able to include an optimization to run the main computational loop pipelined. In order to achieve an II of 1, however, we needed to reorder and remove the dependencies on the same output location. In other words, values on the same row of the input matrix, and include a pragma forcing a false dependency. Our first attempt at reordering was changing the COO format from being in row major format, which means that the data in the arrays are sorted by row number, to being in column major format, where the arrays are sorted by column number. The goal with this was to remove the dependencies by interspersing computations on the same row with those in the same column, ideally spacing them out far enough from one another so that the operations don't overlap. After determining that the multiply accumulate operation takes 8 cycles, we realized that we still had an overlap in dependencies. This overlap, since we force an II to be 1, means that the value assigned to the output will not be correct, leading to an incorrect result. In this example, we can see that 2 operations on the same row that should be spaced 8 elements apart to avoid overlap are only 3 elements apart, resulting in an incorrect output. This means that we need to come up with a different preprocessing solution. We tried many different iterations where some still produced incorrect results or resulted in a significant increase in max latency in our simulations. We finalized upon the preprocessing algorithm shown here. In this algorithm, we space out values from the same input row by the maximum of either the number of rows with non-zero values or 8, depending on the size of the matrix. Once we move on to the next row of the input matrix, we start again at the first available element. Any empty locations in the COO format are filled in with dummy values, indicated by a row value of -1 that aren't taken into account for the calculations. This sacrifices some memory at the benefit of reducing maximum latency.
Another optimization we did was to split the computations among different processing elements so the preprocessing and main SpMV computations could be done in parallel. In order to do this, we split up the input matrix by row into the number of processing elements. In the case of this example, we are splitting up the matrix for 2 processing elements. In this slide, we are showing a figure with normalized max latency and area usage as we change the number of processing elements. This data was obtained from the Vivado HLS synthesis reports when running simulation. From this, we see significant speedup at the cost of a constant rate of resources. As we reach a higher number of processing elements, we can see that the number of additional resources used increases as well. We can also see that the latency begins to saturate around 20 processing elements, suggesting that a more significant speedup may not be worth the cost of memory. For the size of our matrix, however, even with 25 PEs, we did not exceed 75% of any of the resources. Regarding larger problem spaces, more consideration would need to be given to the trade-off between max latency as well as area usage. While the results in the previous slide show that we see a decrease in max latency as we increase the number of processing elements, it does not mean much if it is not a performance improvement over our original implementation in original format, which we refer to as dense, since it is performing the same operations as a dense matrix would. In addition, we wanted to compare performance improvement to our original implementation in COO format without pre-processing or optimizations. From these figures, we can see linear performance improvement over both dense and COO baseline. For COO baseline, since our unoptimized baseline is slower than our dense implementation due to pre-processing overhead, we see an overall greater speedup. As seen in the graphs, we see up to a 67 times speedup over our COO baseline implementation and up to a 50 times speedup over the dense implementation. Even with a single processing element, we see a speedup over both implementations, showing that our optimized implementation indeed results in beneficial performance. The PageRank algorithm used by Google Search to rank web pages in their search engine results is implemented as an iterative SpMV kernel. It works by counting the number and quality of links to a page to determine a rough estimate of how important the website is. A web is represented as a directed graph with web pages as the vertices and hyperlinks between them as edges. The algorithm implementation takes a normalized and transposed version of this matrix called the adjacency matrix and performs iterative SpMV on it until convergence is achieved. The vector result from this computation contains the ranks or importance scores of the web pages in the web. The graph on the bottom right depicts this result, with website C being the most important since every other website in the web links to it, followed by B, A, and then D. This algorithm serves as a critical application of the optimized SpMV kernel, since the same matrix is used to perform the SpMV computation several times, thus amortizing the preprocessing overhead and showcasing the benefits of speeding up the SpMV kernel itself. These are the results of running the PageRank algorithm with the parallelized version of the SpMV kernel. As seen before, the maximum latency decreases as the number of PEs increases while the resource usage goes up linearly. At large numbers of PEs, we see a saturation in max latency, giving us Pareto optimality between resource usage and performance improvement. The speedup graph, on the other hand, changes from being linear to being logarithmic, since the optimized kernel is now only a part of the complete program. Again, we see a saturation in the speedup with a maximum speedup of about 10.72x.
Once the code optimizations were completed, we synthesized the Verilog file using Vivado HLS tool. The synthesized Verilog RTL was then fed to Vivado. Vivado then generated the bitstream file that contains the configuration bits which were sent to the LUTs and switches on the FPGA in order to configure or reconfigure the FPGA to become the SpMV accelerator. The C++ host is run on ARM processor present on Z board, and FPGA is now working as an SpMV accelerator. The program was responsible for invoking the hardware module, that is the FPGA, communicating with the module through input and output FIFOs, and then verifying the results.
Here's an example of the standalone SpMV kernel with 25 PEs running on the FPGA. If it passes, it means that the correct results get communicated from the FPGA accelerator to the ARM processor. It takes about 2.7 milliseconds over here.
Here's an example of the PageRank algorithm running on the FPGA. This uses the SpMV kernel iteratively. As we can see, this also passes, giving the correct ranks for the web pages and taking about 6.5 milliseconds.
As discussed earlier, we implemented logic to preprocess the data before it was fed to the SpMV accelerator. Since this preprocessing needs to be done only once for several iterations of the computation, for example, inside the PageRank algorithm, we can perform the preprocessing outside the hardware. We were able to analyze the regular matrix vector multiplication had an execution time of 7.5 milliseconds, while the optimized COO SpMV accelerator shows an execution time of about 2.5 milliseconds. The speedup is also reflected in the second graph, which shows the execution of PageRank program on FPGA using our SpMV accelerator.
As the project converged, it was important to summarize our learnings. We learned a lot about being hardware aware while optimizing kernels to be implemented on hardware devices like an FPGA. We understood the importance of ordering data to remove inter-iteration dependencies to be able to take full advantage of pipelining. We also understood the relationship between partitioning the right arrays to unroll the loops correctly. When our SpMV function was not working as expected with parallelization, we realized the importance of being able to instantiate the same function multiple times to be executed in parallel, and also learned about a pragma that allows us to do this. With the results of the PageRank algorithm execution, it became more evident that optimizing a bottleneck subkernel can lead to huge performance gains in the overall performance of a program. Finally, studying the HLS reports revealed the trade-offs between reducing latency and increasing resource usage. Thank you.